All right, hello everybody. It's October 28th here in Calgary, Alberta, and we're going to talk about linear regressions outside. The weather's not too bad, but I felt I needed to wear the old baseball cap, I guess the winter baseball cap, because it is getting a little chilly. We're supposed to have a whole bunch of snow tomorrow, so I'm looking forward to that just in time for Halloween. Anyways, you don't have to worry about any of that because you can watch this from the safety and warmth of your own home, wherever you may be. But what we're going to do is continue our discussion of linear regression, hopefully developing an understanding that's deep enough at this point so we can take a look at the output of linear regression analyses in R and understand basically what they mean. I'm going to start out, though, by kind of doing a bit more math like I was doing in the last lecture with kind of the general theme of R being a magic number. R is our correlation coefficient. It's that quantity that we've talked about at some length already, but it can also represent a number of different things. But one of them, and we'll get to at least a couple of them in this lecture and a couple more in the next one. But if you don't get the reference, if you're not as old as me, which is probably the case, in the 70s, there was this series of videos that they would, or not videos, but cartoons that they would put on the Saturday morning cartoon shows as advertisements. They seemed like advertisements, but they're in the middle of the various shows that we cared about. It was called Schoolhouse Rock, and you may have heard about these before. I actually refer to them when I'm talking about different lexical categories in Linguistics 201. But there was one particular video that it's one of those jingles that kind of sticks in my head after all these years. It was about 3 is a magic number. And it's here if you want to follow the link. But it's cool if you're a math geek like myself and still are fond of your own childhood.
3 is a magic number.
And let's talk about all the different
Yes,
ways that we encounter 3 in life. 3 class.
Somewhere in the ancient mystic trinity, you get 3 as a magic number. The past and the present and the future.
Yeah, we'll stop there. But you can watch the whole thing if you want. And like me, you might get that song stuck in your head too. But apparently this is the very first Schoolhouse Rock video ever, which is fine by me. We don't need to learn anything about the number 3 per se for this class. We do need to learn a little bit about R though, so we might as well get into it. Primarily, R is useful because it can help us predict the value of one variable from another, which is the basic setup we've been talking about here for the last couple of lectures. And the extent to which you can predict the value of one variable from another depends on how correlated the 2 variables are, and that amount is basically captured by this quantity R. That in turn will enable us to draw a best fit line for the values of 2 variables which don't fit perfectly on a line but look like they're pretty close. Or even if they're not close at all, you can still draw a line in there, like we saw with our measures of familiarity and the number of letters in each word for that database we were playing around with last time. So it's with R, you can just come up with an algorithm that applies across the board, and sometimes it's going to look better. The best fit line we draw is going to look better than others. And what determines how good it looks basically is how much error there is in our predictions of one variable on the basis of another. So we're going to be looking at the values of 2 variables which may or may not be closely related to one another. We're going to assume a linear relationship between them, and then also assume that there might be errors in the specific relationship that we have, and errors that kind of get added on top to our predictions that we make on the basis of one variable predicting the value of another. So we're going to unpack our equation for our line by adding these error terms to it to just kind of make the accounting a little more neat, I guess you could say. So by adding an error term to our equation for a line, we're going to assume that the relationship between the 2 variables consists of both signal and noise. And I've referred to those 2 terms before, as I think you already know, but we're going to come back to them again. But basically, if you remember, it would probably be better if I actually showed you the specific example. But if you remember the 2 variables we played around with last time, familiarity and frequency, there's a lot of data points there, and I said it looked like a star cluster, and then we could draw a line right through the middle. Maybe I'll actually show you this here in a second, but the line is going to be our signal, And the sort of variation we get on either side of that line is going to be the noise. At least that's how you can kind of think of it. So the signal in terms of our mathematical equations here is the y equals mx plus b part, but this y includes not only mx plus b, a nice solid equation for a line, but also includes an error term, so a bit of noise or error on either side of that linear equation. And as long as we're doing this, I might as well just go over and kind of recapitulate what I did last time. So I think it's in here, and we'll just plot those two variables next to each other, or on the same graph rather than next to each other, both in their own dimension. So to do this, I need to not only get that data frame, but also attach the variable names, so I can just plot it out like this. Yeah, so plot familiarity versus frequency. Actually, I think I did it. I may have done it the opposite way. But either way, if I go down here and, yeah, plot, let's do it this way. Yeah, plot the best fit line for this combination. And I think I didn't realize this, but I plotted them the opposite way. So let me fix that part first, and plot this as frequency on the x and familiarity on the y. It's always good to make mistakes, so I can make sure that you're paying attention. And then we'll plot this regression line on top of it, right? So you can think of this best fit line as just the predictions, sort of what we can kind of rely on in this relationship between the two variables. Or you can think of it as the signal, as like, well, maybe this is sort of the idealized version of this relationship. So if there were no variation based on some other factors, whatever they might be, this is, the clear connection we get between these two variables of frequency and familiarity. But we don't. We get this variation on either side of the line. So this variation on either side we're going to call error. But the way we're going to think about it is in the y dimension. So based on like this x value, like 10, we're going to make a prediction that, the y value should be over here, like a little bit above 6. But what we get is this one up here. So that's the signal here. That's what we should be perceiving in the noise of life, I guess. And what we're actually getting is a little bit off of that. So there's an error term on top of the signal. But mathematically, what we can do is split it up like this, where the equation for our line, the basic equation for our line, gives us the signal, and then there's an error term on top of that. The reason I'm belaboring this so much is because we're going to keep coming back to this. It's not just today, but in the future we're going to see it as well. So the moral of the story is that in real life, predictions are hard, especially when they're about the future. We got a little bit of past, present, future in the 3 is a magic number video, but at this point, what we really care about is being able to use the past in the present to predict the future. What we can do to make that happen is just focus on the sort of linear part of our connection between y and x, which we've seen before. That's our predicted values of y, or the signal. And we're going to represent that with the y hat notation. So y hat sub I is any individual predicted value of y based on the individual value of x sub I, and also the slope and intercept of this equation. And then y sub I in general is the observed values of y. So that has to incorporate both the signal and the noise in it. And then what we have left over there is the noise part of this, which we're going to kind of shuffle off into this term called error sub I. And that will be the difference between the observed and the predicted values of y. So that's the noise. And to go back to this graphical example, which I probably should have just included in the slides anyways, the error again is just how far off the observed value is from the predicted value for any given value of y, but we're only thinking of it in terms of the y dimension alone, right? We kind of know what's going on with x, and we're trying to use that to predict what's going on with y. Okay, so also mathematically, to give you a different expression for the error term, you can think of the observed values of y as equaling the predicted value of y plus the error term, and by extension, that means that error is going to be the observed value minus the predicted value. And we're just putting it like this because we want to capture it as a difference, but this doesn't mean that the error term can't be negative. Sometimes the predicted value is higher or greater than the observed value, and sometimes it's the other way around. Hopefully you can hear this all right. There's a fair amount of traffic going on, but I'll wait for it to pass before I move on to the next slide. So what have we done? This is a bit of review again, mathematically, but last time we worked through a lot of math to come up with a linear equation for y hat, such that the sum of the squares of the deviations from the line shall be as small as possible. And that's just basically another way of saying that we're trying to minimize the noise here, or we're trying to minimize the overall error in our predictions. So to do that, we came up with a basic equation to show that we want to minimize the square differences between the predicted and observed values in our linear connection between x and y. And you can also think of that, so in one way you can think of this as like minimizing the noise or minimizing the error. We can also kind of think of it in graphical or spatial terms, I suppose. It's sort of like finding the average in 2 dimensions, like what line gets the least far away from all the paired values in a data set. And to once again go back to this equation or example, this looks like it cuts right through the heart of this messiness in the data, right? It's supposed to be the line that's the least far away from all of these data points. So it's sort of like an average, like a mean, but we're getting it in, like I said, 2 dimensions. We're considering both the mean of x and the mean of y, and also the variation we get in those 2 dimensions as well. So that's how we get this best fit line sort of conceptually, and thankfully we worked out the math for how to do that exactly, or somebody else worked out the math and we just kind of copied it, and either way it's encoded in R, so we don't have to do it from scratch again. But what we came up with was this equation for a line. The 2 parameters we care about are the slope, which is equal to R times the standard deviation of y divided by the standard deviation of x, and then the intercept, which unfortunately is a little bit more complex, but it's basically the mean of y minus the slope times the mean of x. So like I said, we're kind of taking into consideration both the mean of y and the mean of x as we make these calculations. And now I've got a street cleaner just zipping by, so hopefully you can hear me as I'm still speaking, but I'm not going to say anything important for the moment until he's gone. But I will say again, also as a review, it's interesting that when we come up with this term, what we wind up with is a bit of a measure of sort of the rise over the run here, because we've got the standard deviation of y divided by the standard deviation of x down here on the bottom. Anyways, our equation for the predicted values of y looks like this. It's just y hat sub I equals the slope times x sub I plus the intercept here. And I'm not going to walk you through all this over again. That's where that comes from. It's still, as you can see here, a bit of a confusing mess to express it this way. So I'm going to simplify it one step further. And in so doing, it will become even messier than it was before until it becomes nicer at the far end. So this is kind of as ugly as the math will get in this class, and I kind of apologize ahead of time, but then really I guess I should do a kind of Canadian sorry but not sorry, or sorry but not sorry, because it's going to pay off, I think, by the time we get to the end of the process. All right, so here we go. Here's our equation to start off with. We have y hat sub I equals the slope, this stuff, times x sub I plus the intercept. And what I want to do to start off with in terms of simplifying this mess is to subtract the mean of y from both sides. And so now what I've got is the predicted values of y minus the mean of y equals the slope term times x sub I minus the slope term times the mean of x. So that's kind of interesting. It's already looking a little bit nicer. So one thing I can do here is factor out this slope term, r times the standard deviation of y over standard deviation of x. And I can collect this stuff over on this side as x sub I minus the mean of x. And it's looking even neater here too, because I've got kind of similar expression for y and x on both sides, right? In this case, I'm looking at the predicted values of y hat, and in this case, I'm looking at observed or known values of x sub I, but I'm subtracting the mean from both of them. So what, if anything, can we get out of that? Well, it turns out we can collect this standard deviation of x term into this expression in parentheses, and I'm getting x sub I minus the mean of x divided by the standard deviation of x. And if this looks familiar to you and you're like, hey, I know what that is, then great, you should, because we've talked about this expression at some length, but I'm not going to spill the beans and tell you what the answer is until I do something else, which is to move this standard deviation of y term over onto the left side by dividing both sides of the equation by the standard deviation of y. And now what I've got is the y hat sub I term minus the mean of y divided by the standard deviation of y. This looks awfully similar to what's in this parenthetical expression here. They're connected by r, and what these guys are, ha 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 ha, is the z-scores for two different terms. So we've got the z-score for y hat sub I equals r times the z-score of x sub I, which I think is maybe one of the coolest expressions of r. We could even take it a bit further and say r equals the z-score of y hat sub I divided by the z-score of x sub I. But we'll leave it as this for now. But it's just cool that basically it's the ratio of those two z-scores of our two different variables. The one we're predicting divided by the one we're using to make the predictions. Or if you think of it as rise over run again, it's the z-score of the predicted values of y, the rise, divided by the predicted values or the observed values of x, the run. So our best fit line equation can be converted into this expression here, which is very nice and tidy indeed. And again, what this means is that if you want to get the z-score, if you want to be able to predict the z-score of y, you just multiply the z-score of a particular value of x by r. And r, again, is the correlation between x and y. So that's, I think, as simple as r gets, and is, like I said, maybe the payoff of why we're doing this sort of thing. And I think I said before that this is going to be kind of as messy as the math gets in this class. I lied. Or rather, I'd forgotten about there's one other case that I'm going to show you where it gets messier than that. And again, I'm doing this because Keith in his textbook throws out a number of expressions like this, which seem kind of to fall out of the sky. But we're scientists. We don't believe in, depends on your religious beliefs, but we don't take manna falling from heaven for granted. We want to find out where it comes from. And we want to find out where this math comes from too, because somebody somewhere along the way worked out all the details. So I'm going to walk you through the primary details of some of the R-based equations that are presented in Keith's text without just asking you to take them for granted. And then along the way, or at least by the time we get to the end of the next lecture, we'll learn that another magical property of R is that it can measure how much variance X can account for in Y, which is also quite cool. So how do we account for variance, or how can we use R to account for variance? And what I want to do is start off with our new version of the equation for the best fit line. And this is the slightly simplified version, not the one we wound up with at the very end of that process. But we're looking here at sort of the deviation from the mean of y hat sub I, and then also the deviation of x sub I from the mean of x. And then we're multiplying this x term here, this collected x term, by the slope of our best fit line. Okay, so what we want to find out, starting from here, is how much residual variance is left after our best fit line has made its best prediction of the y values from the x values, i.e. how much variance is there in the error terms in our prediction equation. So remember that our error is basically the difference between the observed values of y and the predicted values of y. So we're going to start off with an expression for the variance of the error terms in y as this, which is a little bit of a mess, because what we're doing is we're looking at the sum of the square deviations of the observed minus the predicted values of y all over n. So we're not getting the mean directly involved here as we normally do in calculating variance, but we can kind of sneak it back in by just looking at those deviations independently, like this. So we have the difference of the observed values of y minus the mean of y, and then subtract from that the difference in the predicted values of y minus the mean of y. And then we'll take this difference and square it and sum that up and then divide it all by n, or the number of observations we have in our sample. So we're going to start off with this as our measure of the variance in the errors. And again, we're trying to find out how much residual variance is left after we've made our best prediction. In other words, how much do we have left over that we can't account for in y? How much error is there? at the end of our process. And with, again, the idea that normally we'd like to minimize that error to be as small as possible. And this is where things get hairy, so mathematically, or at least algebraically. But I'm going to take this equation I left off with at the end of the last slide, put it there, and we're going to substitute our best fit line equation for the difference between the predicted values of y and the mean of y, and which is up here, as you might recall. And I've got another street cleaner because today is street cleaning day. So to make sure you understand the math, I'll pause as he makes a lot of noise and heads off to the east. See you later, bud. Anyways, thanks for your service. What I'm going to do is plop that into this second part here. So this is our new equation for the best fit line. We're keeping the first part of this in the sum term the same. I'm factoring out 1 over n here. It winds up being exactly the same. It's just dividing the whole thing by n, but it's going to look like we're multiplying here just to make the housekeeping a little easier to read. Okay, so what I want to do here is where it gets ugly. Let's expand the squared term. So this business in the middle here, you can think of this as like a minus b squared. And when you square that whole thing, if you remember from, high school math class, it's a squared minus ba plus b squared, that sort of thing. We're going to do the exact same thing here. So this gets multiplied by itself. That's squared. This gets multiplied by itself, and the sign changes because you're multiplying a negative by a negative, so that's over here. And everything here gets squared as well, right? And then we multiply this by this, and this by this. So that winds up giving us what we have here in the middle, this 2r times the standard deviation of y over standard deviation of x, which we're getting from here, times this guy times that guy. Okay, so and since we're getting basically two negatives, positive times negative is negative, and then negative times positive is negative, it's minus 2r in the middle there. What can we do with that? All right, well, we have to collect our terms here, so I'm going to apply the summation, not over the whole thing, but just split it up because we're kind of adding things within this big summation term, and then summing them up is kind of the same thing as summing up the individual terms and then adding them up at the end. So you kind of cheat that way by putting the summation terms here in the middle. And in so doing, maybe some of this stuff here starts to look familiar to things that we've seen before. Like I said, this is as messy as it gets, but all of a sudden we can kind of quickly clean things up. Okay, so I'm going to start from this on the next slide, and then say, look, a lot of this stuff in here should look familiar. So number 1, the variance of y is this guy right here. Number 2, the variance of x is this guy right over here. And then number 3, the covariance of x and y is this stuff right in the middle here. And we can actually take a step further and say that's equal to r times the standard deviation of x times the standard deviation of y. And we can kind of substitute all these terms, which have just variance or standard deviation in them, or r, and then all of a sudden we get an equation that looks like this. And remember, this is supposed to represent our variance of the error term in our predictions. So we're almost all the way there. This looks cleaner than this, but we can still kind of simplify this a bit by going from here to something that looks like this. So this part at the beginning will stay the same. This one in the middle will cancel out these standard deviation of x terms. And then if we multiply the standard deviation of y times the standard deviation of y, we get the variance of y times 2r squared, because there's two r's in there multiplied by each other. And then at the end, we can cancel out the variance of x and just leave the variance in y. Okay, what does all this mean? We can even go a bit further, as you might be able to see here, because we've just got the variance of y in different sorts of expressions here. So collect these two guys into just a minus r squared times the variance of y. And then I'm going to factor this part out, the 1 minus r squared part, and say 1 minus r squared times the variance of y equals the variance in the error term. Okay, so that looks relatively clean and manageable after all that work. I'm going to do one step here which might seem a bit odd, but it'll come up again a little bit later. And I'll take the square root of both sides of this thing and say that the standard deviation of y equals the standard deviation of the error term equals the standard deviation of y times the square root of 1 minus r squared. And the only reason I'm doing that is because that square root of 1 minus r squared term has a special name. It's called the coefficient of alienation, which, as far as I'm concerned, would be a great band name or maybe a great album name. So if you ever create such a musical creation, all I have to say is at least put me in the liner notes. Anyways, there's also something called the coefficient of determination, but actually I'll come back to this and kind of say this coefficient of alienation kind of converts standard deviation of y into the standard deviation of the error term. The coefficient of determination is kind of a more positive way to think about this relationship. So let's go back to this 1 minus r squared times the variance in y equals the variance in the error term. And let's solve for r. What do we get when we do that? Well, to do it, first of all, we can divide both sides of this equation by the variance in y. So we have 1 minus r squared equals the variance of the error over the variance in y. All right. And if we just do some addition on both sides of this equation, we're actually subtracting this from both sides, then adding r squared to both sides. We just kind of switch things around a bit. We get r squared equals 1 minus the variance in y error divided by the variance in y overall. And now we can say r squared is the coefficient of determination. All right, so let's take a look at this here for a second and try to think about what this is telling us. So let's say we had a perfectly predictable relationship where there was no error in the y terms whatsoever, and this guy went to 0. Then we'd have r squared equals 1 minus 0 over whatever the variance in y is. This term would go to 0, and r squared would equal 1. So in that case, if there are no error terms at all, if you have a perfectly predictable relationship, then r squared equals 1. Let's say, on the other hand, that you can't make any predictions at all, and all of your y variance is error variance, then this part of the fraction equals this part of the fraction. So this simplifies to this variance in error divided by the variance in error on the bottom, and you get basically 1 for this entire fraction. So we have 1 minus 1. That's equal to 0, and r squared will be equal to 0. So if you have a totally unpredictable relationship where everything's just an error term, then r squared equals 0, and you can't make any meaningful predictions at all. So r squared is the coefficient of determination. It can range from 0 on the low end to 1 on the high end. It basically tells you how much of this relationship you can predict, how much you can determine using this correlation coefficient. So it's the percentage of variance in y that is not random errors in our prediction, i.e. the signal. It's how much variance in y that you can account for, basically, using this sort of best fit line relationship. I'm going to say here that this is the end of this portion of the lecture, but I will tell you that R tells you a lot of different things when you ask it to run a linear regression analysis, and one of those things is what the value of R is. So we'll see that directly as we go through a couple of examples of how to run a linear regression in R and how to interpret its results. But for now, I'm going to stop there, and so we'll take a break from the math, and we'll do some R commands in the next short video just to get a sense of how we can actually apply this knowledge to something that might be meaningful to us, like. All right, so I'll see you then.